Maybe now you know it better. All right, so let's just look at that power in electric circuits, and it'll describe a little bit how it's determined. And, basically, it's just the amount of charge that moves from the terminals of some power supply, or you can think of also in terms of that passing through a resistor, and that's what we'll look at here. There's some device here. I got a question mark. We don't know what it is, and so in the time interval dt, delta t or dt, the amount of charge that passes through this this device is I times dt, right? And so this is basically, you can think of it, we have a voltage, we have a charge that's moved from one place to another, so we're doing work. So it's the electric potential energy decreased by magnitude, by amount of change of potential is equal to the change, the charge, this amount of charge that passes through, not really a change of charge. This amount of charge that passes through this device times the voltage across that device. And we need to make the substitution here for the amount of charge that's moved, the infinitesimal amount, if you want to call it that. It's I times some interval of time times the voltage that's across that device, the mystery device. So the decrease in potential energy from A to B is accompanied by transfer energy, of course. We're doing some work. And see, it's basically the power associated with that transfer. It's a rate of transfer. It's just basically the rate change of the potential energy per time. It's just analogous to that in the mechanics in 207. You're doing work and something's changing potential. And so then as a result, it's current. Basically what I've done here in this equation is divided both sides by the time interval dt. And so we're just left, the power is equal to du dt, which is equal IV in this case. VI. There's multiple ways of writing this, actually. A lot of situations when you're talking about the amount of energy that's dissipated, let's say through a resistor, such as here, you usually want to write this as I squared times the resistance. I mean, that's the same thing, right? V is equal to IR, that's Ohm's law. And a lot of times that's referred to as ohmic losses. And where the amount of energy or this amount of power that's generated by a power supply is typically written as VI or IV. I mean, they're equivalent, but in some ways they're not. If you're talking about dissipation of energy over very long distances of wire, 100 kilometers, and then you really have to worry about these ohmic losses. And it's the amount of current that passes through these wires. It's where you just lose all this power. So, what a lot of companies do, I mean, these power companies, they increase the voltage and decrease the current. And you get the same amount of power, but there's just less ohmic losses. One of the reasons why Tesla won the battle of currents against Edison is just for this reason. It's just much easier to transform, from a high voltage to a low voltage and vice versa using AC as opposed to DC, which we'll talk about later, but it's just related to transformers. And, the reason also because magnetic fields are produced from currents, which, again, I'm getting ahead of us. So anyhow, the unit of power, volts times amps. You just go through this, and it's equal to joules per second, which is watts. Standard thing you say in New York City, when you say hello to someone, that you say watt. So hopefully no one's here from New York City.
That was an amazing joke. Oh my gosh, thank you.
It was so great. As a New Yorker, that was the best.
Oh, okay. I'm glad I didn't hear too many boos. I better move on while I'm ahead. So I want to do an example here. We have electric heater constructed by just applying a potential difference, 120 volts across a nichrome wire that has total resistance of 8 ohms. And so we want, we find the current carried by the wire and then the associated power generated by the heater. So the current, that's something we can do this using Ohm's law. And so the voltage is 120. The resistance is 8 ohms. And so from that, we find that it's 5 amps. And to determine the power, what I'm going to use is the I squared R relationship. You guys see how it's I squared times R. I mean, we said it's V times I, but V can be substituted for IR. And so we have this relationship. This is, typically used, just to consider ohmic losses too. But this is what we're really talking about. It's the amount of power generated by the heater, the amount dissipated. And so we already know what the current is. That's 15 amps. And the resistance is 8 ohms. And as a result, we can calculate this pretty easily. And it's 1.8 times, well, it's 1.8 kilowatts. So we have time. Oh, yeah, I have time. All right, keep going. Any questions about this? Okay, let's move on. One more interesting problem here. So, immersion heater is a resistor that's inside a container of water, basically. And its energy is delivered to the immersion heater, and it raises the temperature of the water. Its energy just leaves the surface of the resistor by heat, going into the water. When the immersion heater reaches some constant temperature, the rate delivered to the resistors, to the water, kind of becomes constant. What we want to do here, though, is just assume, if there's no energy losses, then basically heater could just turn off and the temperature would stay at 50 C. But what we want to look here is how much power is needed to increase the temperature of the water from 10 degrees C to 50 C. And over this time period of 10 minutes. And we're restricted to use a constant voltage, 110 volts. And the amount of water is 1.5 kilograms. All right, so the amount of power, electrical power, we can calculate. It's pretty straightforward, because do we have everything we need for this? There was a resistance here. Hang on. Okay, sorry. All right, so this is the amount of power dissipated by the resistor, which is unknown. We're just doing like a V squared over R in this case in terms of the form of the power dissipated. And that for the water, if you guys remember from thermodynamics, or this thermal from 207, it's just power in terms of that into some material in terms of heat. It's this Q divided by the time, the duration, which is given to us as 10 minutes or 600 seconds. And the Q value is dependent on a few things. It's dependent on the mass of the water, the heat capacity of water, and as well as the temperature change. Different T than here. Delta T here in the, sorry, I keep forgetting my mouse is not always the place I think it should be. The delta T here is the time, Q is the heat or energy transferred to the water. M is the mass of the water. C is the heat capacity of the water, per kilogram in this case. So think of this the amount of energy needed to raise the temperature by a unit temperature. In this case is C. And the temperature change is delta big T. So what we do is that we equate these powers together. We assume it's 100% efficient. No energy is lost. So the electrical energy equals the thermal energy. So we now can equate these equations together. In reality, it's probably some efficiency factor here, but we'll just ignore it for now. So we have V squared over R is the electrical side, and this is our thermal side. So now I think we have everything we need in terms of the solve for the resistance of the heater. So the next equation, basically just multiply through times the resistance. And we get this relationship here by both sides by the Q value. And of course, we have the delta time at the top here. Everybody okay with this equation, with this relationship? Okay, take that as a yes. All right, so the only thing left to do now is to plug in the values that are given to us. The 1.5 kilograms for water, the temperature difference, that's 40 degrees C. And the voltage is 110. So we'll just plug in these values and we get something a little bit under 30 degrees. 30 ohms for this case here. Of course, there's 600 seconds in 10 minutes. This did the conversion automatically. 10 minutes is chosen here. It's a little easier to calculate.
Did we have to convert to seconds here?
Well, that's the SI unit. Yeah, I think, see, why would you not want to do that? Yeah, I mean, the fact that power is just defined as joules per second, watts, I think you would want to use seconds here.
Cool, thanks. That makes sense.
Yeah. Yeah, it'd be a strange units otherwise. I don't know if we have time to do this, but let's maybe move on. Well, in terms of when you see a light bulb come on, at least in the case of incandescent, the brightness is proportional to the power dissipated by the filament. And so I want to look at this, and hopefully we'll have time to do a little demo. Hopefully you can see it. Sort of been the problem with doing demos. So what is the power dissipated in R1 and